Now that we know a little bit more about the overall shape of a molecule, it's time to consider the overall polarity of a molecule. Polarity simply means that something will have two poles, a positive end and a negative end. And we've already talked about this with singular bonds. So if we take a look at, say, just this single bond, we can see that the electrons are not distributed equally. That one end actually has a bit more electron density than the other end. And we can use these symbols, partially negative toward the more electronegative atom and partially positive toward the less electronegative atom. Now, if we only had a molecule made of this one bond, then what we would see is that opposites in fact attract. So if we brought two molecules close enough together, we would actually get an attraction between the positive and the negative ends of two molecules. Now the problem is that when we have a molecule with multiple bonds on the inside, we have to consider the whole electron density for the whole molecule at the same time. In this case, it's kind of like there's an overall tug of war. We have to figure out where the electrons are going to end up. Let's take a look at an example. Here are two different molecules. You can see that both molecules have multiple bonds. And around the outside, you can also see how the electrons are distributed in each. In the first molecule, you can see that the electrons are fairly evenly distributed amongst the whole molecule. Whereas in the second example, we can see that the electrons are unevenly distributed. That's why we have this big red cap along the top that indicates that the electrons are spending more time up there than they are at the bottom of the molecule. So what creates this either even or uneven distribution? Well, that would be symmetry. Whether or not the molecule is symmetrical in shape or non-symmetrical in shape will determine whether or not the individual bonds cancel out in their little tug of war. So in the first shape, we can see that essentially it's an extremely symmetrical shape. We have all of the same things bonded to the center of the atom. And when we have all the same things bonded to the center of our atom, well, it's going to all cancel out around the outside. And we're going to evenly distribute the electrons throughout. Whereas in our second shape, we would call this non-symmetrical. We don't really see the shape being balanced out top and bottom, so there's going to be an overall uneven distribution of those electrons. So let's summarize. How do we decide whether or not a shape is symmetrical or non-symmetrical? And therefore, how do we determine whether or not it's polar or non-polar? Well, first of all, again, you're going to need to look at the central atom. And then simply decide, do I have all of the same things surrounding the outside? If the answer is yes, then your molecule is symmetrical. And not only is it symmetrical, but it will be non-polar. What if you have different things surrounding the outside of your atom? Well, then your molecule is non-symmetrical. And if it's non-symmetrical, the electrons will not be evenly distributed, and your overall molecule will be polar. Now, once again, polar means that the molecule will be sticky. It'll be attracted to other molecules that are also sticky or polar. Let's take a look at some examples, and you can actually determine this from a Lewis dot structure. First, again, I want to take a look at the central atom, in this case, the carbon. And take a look at what's actually attached to that carbon atom. I have 4 chlorines bonded. It's all the same stuff all the way around. In this case, because it's all the same things surrounding the center, I would not only call this molecule symmetrical, but it's also going to be nonpolar. What about this example? Again, carbon is my central atom. Take a look around the outside. In this case, I have 2 hydrogens and a doubly bonded oxygen. That's not the same stuff surrounding my molecule. So because I have different things attached to my center, this becomes a polar molecule. Now we have a little bit of extra work to do if our molecule is overall polar. Again, this molecule is going to be considered to be sticky, so it will stick to other similar molecules. Now, code word for sticky, of course, is polar. That's really the proper way of saying this. We will need to add a dipole arrow to show the overall dipole moment. In other words, in which direction are the electrons going to be distributed? Where are they spending more time versus where are they spending less time? In this case, we want to make sure that we point the point of the arrow toward the most electronegative atom. In this case, it's already highlighted, it's oxygen. So we'll draw one arrow through the entirety of the molecule, showing that in this whole molecule, the electrons will be spending more time on the oxygen and less time by the hydrogens. So over by the hydrogens, it will be partially positive, and over by the oxygen, it will actually be partially negative. And these molecules can line up one to another, being attracted to one another. How about one more example? Good old H2O. Again, I want to take a look at the central atom. In this case, it's oxygen. Oxygen has 2 lone pairs and 2 bonds. Is that the same stuff all the way around the outside? Why, no, it's not. So because I have different things around the center, and what makes this example special is to understand that lone pairs also count as things to consider. If you have lone pairs on that center with bonds, it's not the same stuff all around the outside, and it instantly makes your molecule polar. So pro tip here, if you see lone pairs on your center, basically pretty much 100% of the time, your molecule will instantly become polar. Again, we would need to add a dipole arrow. The dipole arrow is going to be drawn in the direction of the most electronegative atom, in this case, oxygen. So the oxygen side of this molecule will be partially negative, and the hydrogen side of this molecule will be partially positive. And again, these water molecules can line up next to each other and become attracted.